All right, so we're going to do this application of exponential equations, and then we'll look at the logarithmic equations that we're going to solve. And I have to go to a meeting at 10, so we got 20 minutes. All right? Yeah, you have this, right? Okay. When a living organism dies, its carbon-14 decays. The half-life of carbon-14 is 5,730 years, so the amount of carbon-14 remaining at the time t is given by this formula, where p is the mass of the carbon-14 that was present initially. The function m can be used to determine the age of fossils and some relics. It is determined that a mummy has lost 32% of its original carbon-14. When did the person die? So if he's lost 32%, then what? %68 still there, right? Okay, so they don't tell us P or M, all right? But they do. Okay, they tell us that the amount remaining is 68%, correct? Because if 32% is gone, 68% is remaining. Well, if I have 68% remaining, I can do two things. I can say that I have 68 out of 100, or I have 0.68 out of 1. Okay, and the easiest way is use the 0.68 out of 1, so m of t is 0.68, and my starting amount is 1. Because they don't tell us the original amount, they just give us percentages. So to find the answer to this, we are going to well, we could graph it and find the intersection point, but on Friday we learned how to use logarithms to find the answer to this, and you don't have to go hunting for an intersection point when you can use logarithms. All right, so we move the t over 5,730 into front, and we get, so we're going to divide by the log of 0.5 and multiply by 5,730. And you should get that that person is approximately 3,188 years old. And you could use natural logarithms too, like I did in my previous example. Okay? Whichever method you prefer, whether the common log or the natural log. All right, solving logarithmic equations. All right, first thing to do these is simplify so you only have one logarithm on each side. That means we have to use the product rule and the quotient rule at times, or the quotient rule, not necessarily both. But what does this plus sign mean here? Multiplication. So that means we're going to have the natural log of 4x minus 1 times x plus 2 equals, and I'm going to rewrite this as the natural log of x squared. So we have natural log here, natural log here. So what does that mean? Okay, they kind of cancel out, because if these two things are equal to each other and I have the natural log of one thing equal to the natural log of the other thing, then these two things, well, which I'm going to multiply this one. So we need to FOIL this. 4x squared plus 8 minus 1 plus 7x minus 2 equals x squared. So then all I have to do is solve that quadratic equation, right, which we've solved many of them. So we subtract x squared, so we get 3x squared plus 7x minus 2 equals 0. And thankfully this is a quadratic equation or a quadratic function that cannot be factored, right? So what do we need to do? Okay, either complete the square or do the quadratic formula. So you go ahead and finish that one by doing. Okay, so we get these two exact values, negative 76 plus or minus square root of 73 over 6, and these two decimal values when we approximate them. All right, now, will they work when I plug them back in? And the answer is one of them will. Okay? Because when I put the negative 1 into this one here, negative 2.59 plus 2 is a negative number. Or if I put it in over here on the right-hand side, I cannot take the natural logarithm or the logarithm of a negative number, so this one doesn't work. So my answer then is going to be the exact value of x equals negative 76 plus the square root of 73 over 6. There's only one answer, and it is that exact value that we're going to use for our answer. So you have to remember that on these, you've got to check them because we cannot take the log or natural log of a negative number. Okay. All right, awesome. Number 10. What do we do first here? There's not dividing on the right, because that says 8 minus. It would have to be the natural log of something minus the natural log of something for us to divide. Okay. Another option. Max. Correct. We're going to add natural log of 2x plus 1 to both sides so that they're on the same side. And, oh, what do we notice about these two? They're the same. So that means I have the natural log of 2x plus 1 squared equals 8. All right? Now, there's two ways to do this. One is much easier than the other. Okay? So we could change it to exponential right now and say that 2x plus 1 quantity squared equals e to the power of 8, and that would be okay. All right? But the easier way for you would be to take the 2, move it to the front, which means then I can divide by 2. And that would be the best and the easiest way to answer this question. Because when you start taking square roots of powers, sometimes we get messed up. We don't like to be messed up. So, e to the 4th power equals 2x plus 1, and we solve. because all I did now is change it from logarithmic form to exponential form. The base here is e for the natural log, so e to the fourth power equals 2x plus 1. So we get e to the fourth minus 1 divided by 2 equals x. And we're going to leave it like that unless they ask me for an approximation of what that number is. And if you want to find the approximation also, just so that you have an idea of what that value is.
We don't have to solve that?
Well, that's a number.
Yeah.
Right. You could, if you wanted to, find the decimal number of that. That's fine, but you don't have to. Okay? Morning. Okay? That should be easy. That should be easy. All right, go ahead and do 11. Okay, so we add log both sides. So we've simplified it so we have a simple logarithmic equation. So now we're going to change it to exponential here. Change it to exponential here because 10 to the first power equals x squared plus x minus 2. Okay. All right. Okay. So we factor, well, I subtract 10 from both sides, factor. You should get negative 4 and positive 3, and you can't take the logarithm of negative 4, but you can positive 3, so we x out the negative 4, and we start the 3. Okay?
I'm going to do that from now on.
Okay? All right.